Okay, so we've gone on and we're in chapter 6 now with gas laws. So I don't know how to scuba dive, but let's say I just went and had a huge snorkel like this. Would this work? Would this work if I just said, hey, if I want to swim 100 feet down, I can just go and I can breathe through a huge snorkel? Will this work? The answer is no. This will not work because my lungs down there's a pressure of 1 atmosphere of pressure. Every 33 feet or 10 meters of water is equal to the same as in 1 atmosphere. So then there is 3 atmospheres from this. So that means in my lungs there would be a pressure of 4 atmospheres, 4 times atmospheric pressure, and then they're at sea level. What would happen if I would try to breathe? All of the air would leave my lungs, and I would have a collapsed lung. Airflow goes from high pressure to low pressure and would just go right up the tube. Wouldn't work very well. So would that work? No, no, it would not. So with that, we mentioned pressure. Pressure is defined by force divided by area. So if you feel like you're under pressure, what does that mean? It means a force divided by an area. The SI unit is a Pascal. That's a Newton per square meter. You might be familiar with a PSI. That's a pound per square inch. Um, Also, sound. So sound is a pressure wave, a longitudinal wave of pressure, and we can hear that in our ears. So it's a delta P, and the change in pressure from the longitudinal wave of sound is how we hear things. So there's pressure. I'm going to mention a couple of the laws. So the book goes in great detail. It's more important that we get to the ideal gas law. But so start off, we have Boyle's law. Boyle's law is sometimes described as P1 D1 equals P2 V2, and which also means that pressure and volume are inversely proportional. That means when one goes up, the other one goes down. An example of that is like how much fun I'm having versus my bank account balance. I'm having lots of fun, I'm taking trips, I'm going out. What happens? My bank account balance goes down. Say I decide to do extra work, say I stay in, I make some crock pot meals, then I'm saving money, my bank account balance goes up, but I'm not having as much fun. So that's inversely proportional. One goes up, one goes down, and one goes down, the other one goes up. That's the inverse. So with pressure and volume, so like if the pressure decreases, the volume increases. So if you blow up a balloon and then go up a mountain, you can try this out. You can try this on Haleakala if you want. Take a balloon, blow it up a little bit, and then drive up the top of Haleakala. The balloon will get bigger because the external pressure has gone down. Okay, going on Charles' law. Charles' law, volume is directly proportional to temperature. In this case, when one goes up, the other one goes up, and when one goes down, the other one goes down. That's directly proportional. Hot air balloons work this way. We don't have hot air balloons in Hawaii, but the way they work is you have a droopy balloon and you heat it up, and then suddenly the air expands, and now you have a hot air balloon. And then they float by the displacement of the air. That's called buoyant force. The weight of the air that's displaced equals the force that they can, the buoyant force, and then they can float. So one thing with temperature, though, when we deal with gas laws, we have to use absolute temperature, and the temperature scale that we use is Kelvin. There's other absolute temperatures. Rankine, for instance, is an absolute temperature using Fahrenheit, but we use Kelvin. Most people use Kelvin. Rankine is only used by American engineers, to be honest with you. So Kelvin is degrees Celsius plus 273.15. So what is absolute zero? So 0 Kelvin, it means no translational energy. So molecules they can move around in terms of Cartesian coordinates, length, width, height. They can move around that way. That's known as translational. Molecules can also spin. That's known as rotational. They can also vibrate. That's known as vibrational. So they can shake and dance. That's a vibrational energy. So at absolute zero, that means there's no translational kinetic energy. So molecules can still move. They can still dance, and they can still rotate. They just can't move left, right, or up or down. They're standing still that way, and that's what temperature is translational kinetic energy. Okay, so and to give you this idea, what is negative 100 degrees Celsius in Kelvin? Well, you just plug that in the equation, minus 100 plus 273, so that's 173. Okay, so Avogadro's law, that means volume and number of moles are directly proportional. So if you want to blow up a balloon, you put more moles of gas into it, it blows up. That's Avogadro's law. Finally, we get to the ideal gas law, combines them, where pressure times volume is equal to the number of moles. R is the gas constant, and temperature. R, if you're wondering, is Avogadro's number times the Boltzmann constant. Boltzmann constant deals with probability, more or less. So R is a combination of two other variables, or constants, excuse me. So, but it's a gas constant, has a value, at these units, has a value of 0.08206. We also need to use it as the unit's 8.314. That's joules per mole Kelvin. So it depends on the units and when you use them, what type of R you use. Okay, so let's do this. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So use the ideal gas law, PV equals nRT, solve for the variable. So we want volume. So volume is nRT over pressure. Then you plug in the numbers, 0.845 moles. R is, oh, that's the wrong R. 0.08206 liter atmosphere over mole Kelvin. I'll put this in parentheses. Temperature is 315 Kelvin. And then pressure 1.37 atmospheres. So let's look at the units. Moles cancel, kelvins cancel, atmospheres cancel, and we're left with liters. And then you just plug in the numbers in your calculator and you get 15.9 liters, like so. Okay, so your turn. Try this out, and it doesn't matter what gas. Pressure is half atmosphere, volume is 50 liters, temperature is 50 degrees Celsius. What's the number of moles? So try this on your own. If not, PV equals nRT. N is PV over RT, which is 0.5, 50, 0.08206, temperature 273 plus 50. And this is the step that people miss on this one frequently. If you put that in your calculator, you will get the answer of 1. Oh, it's going to be 0.9, but rounding up to 1. Okay. So moving on, here is a little bit of a derivation. So M is molarity, moles per liter, N over V, so that's moles per liter. And with the ideal gas law, N over V is P over RT. And so moles per liter times grams per mole of the molar mass, you get grams per liter. That's density. So this way you can solve. So you set this equal to m. So this is, you put that there, and then you multiply it by grams per mole, and that's a molecular weight, and you get that. That's where you, same thing. So you just multiply both sides of the equations by this, and it uses a script m. All right, you multiply both sides by script n, and you see here that this turns into density, so density is that. So that's how you derive that. And density is described that way. Another thing with this, you don't have to memorize any of these, but this is the conversions. 1 atmosphere is 760 millimeters of mercury, also 760 torr. So torr and millimeters of mercury are the same thing. It's about 10 meters of water, or 33 feet of water, 14.7 psi, and 101.3 kilopascals. So if you're converting between unit sets, that'll work there. So calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeters of mercury. So these are given, the density formula, let's go ahead and put it in. So density, then pressure, 755 millimeters of mercury, so times atmosphere over 760 millimeters of mercury. Molecular weight of nitrogen gas is 28 grams per mole. And I'm getting that from the periodic table here. So 28 grams per mole over R, 0.08206 liter atmosphere mole Kelvin times temperature, 125, this is 398 Kelvin. Okay, so now we have to put it into our handy-dandy calculators. And, let's look at the units. So, 1 over moles cancel, kelvins cancel, millimeters mercury cancels, atmosphere cancels, and we are left then, the units is going to be gram per mole, and we get 0.852, grams per liter. Okay, to give you an idea, liquid water has a kilogram per liter, so it's 1,000 grams per liter. So to give you in perspective how this compares to liquid water, liquid water would be about 1,000 grams per liter, depending on the temperature. So this is much less. This is what I mentioned, where the condensed phases have a lot more matter than the vapor phase. Okay, so moving on, let's look at these other pressures. So if we have multiple gases, how does the ideal gas law work for each of them? It's just, they work whatever gas it is. Pressure A is equal to, so P equals nRT. nRT over V is pressure. So if we have mixtures of gases, gas A, say it's oxygen, and it's moles oxygen RT times RT over V. If gas B is nitrogen, pressure of nitrogen is moles nitrogen times RT over V. This is known as Dalton's law of partial pressure. Oh, and the total pressure is just the mixture of them. They add perfectly. Also, mole fraction is the amount of mole of whatever component over the total number of moles. And that means then the pressure of whatever is the mole fraction of that gas times the total pressure. For gases, typically, instead of using X, is used Y. I don't know, I'm not sure why freshman chemistry is doing, or if this is just TRO or if it's something, but typically, and you see this in a lot of government documents too, if you look at, there's a lot of equations in government documents, when the Code of Federal Regulations, they typically use Y instead of X. So if you go and you look at laws, you're wondering what the heck is Y? It's usually the gas law partial mole fraction. X is usually for the liquid phase. Okay, so let's do this. 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 Kelvin. The partial pressure of helium is 341. Partial pressure of neon is 112 millimeters of mercury. What is the mass of argon present in the mixture? So this is what we know. We have a vessel drawn by this cube. And I'm talking about my beautiful picture right here. Volume is 1 liter. Temperature is 298 Kelvin. Total pressure is 662 millimeters of mercury. Pressure of helium is 341. Pressure of neon is 112. What is it looking for the pressure? The mass of argon. We want to look at the mass of argon. We don't know the pressure of argon, but we do know that the total pressure is the pressure of helium plus the pressure of neon plus the pressure of argon, which implies pressure of argon is the total pressure minus the pressure of helium minus the pressure of neon. So the pressure of argon, this is going to be 662 minus 341 minus 112 millimeters of mercury. And what is that? That would be 209 millimeters of mercury. So now we have to do the look for the number of moles. So PV equals nRT. N equals PV over RT. Right? So let's do this. N is equal to PV over RT. So pressure is 209 millimeters of mercury times, get it backwards, atmosphere over 760 millimeters of mercury. Pressure, volume, what is it, 1 liter, 1 liter. R, 0.08206. Liter atmosphere, mole, Kelvin, times 298 Kelvin. And doing this, you get 0.01125 moles argon. And then argon is 40 grams per mole. So I guess it's 39.95. Okay, so then we have grams argon equals moles argon times 39.95 grams per mole equals 0.01125 moles times 39.95 grams per mole, and then we get 0.449 grams of argon. That's what's left over. Okay, so recap with this one. So this is to illustrate the Dalton's law total of pressures. So total pressure is the pressure of all the gases in the mixture. We know the total pressure and the pressure of the two gases. We don't know the pressure of the third gas, argon. So we subtract the other two gases from the total pressure to get a pressure of 209 millimeters of mercury. Then we solve the ideal gas law to get the number of moles. We find out that we have about 0.011 moles of argon. We multiply that by 40 grams per mole to get the mass of argon, which is 0.449 grams of argon. And we are done. Okay. So let's talk a little bit about some chemistry and society stuff. What is dry air? So dry air is air without water. Depending on where you're at in the Earth has about an average of about 1% water vapor in the air, and that is our primary greenhouse gas as well. So without water vapor, the Earth would be much, much cooler than it is today. So you might know this if you go to the desert. It gets really cold at night in the desert, and here it's not so bad here, even where it's really humid. Here or like I grew up in Ohio, it gets in those hot summers, the hot muggy summers. So, but it's more you feel it when it's not there, like in a desert. It's really chilly. That's what the Earth would be like without water vapor. Really hot during the day and really cold at night. But this is what air without water and it is. It's about 78% nitrogen, 21% oxygen, a little less than the percent of argon, and trace other gases like carbon dioxide and just various others. And they're also found at different levels of the atmosphere. For instance, we see a little bit more ozone around the stratosphere. We know that's the ozone layer. We see some of the lighter gases up higher too. But generally speaking, this is what the air is made of. And this is important for us because we breathe oxygen. And I don't scuba dive, but if you look here, this graph, the safe range for us is pretty much at sea level, and in that yellow zone, it gets uncomfortable. I unfortunately get altitude sickness, so I feel that yellow range, and then beyond that, you can die at the hypoxia. That's too little oxygen, and we can breathe pure oxygen at the surface. That's fine, but if you get to about 1.6, so between 1.4 and 1.6 atmospheres of oxygen, you can't. I've never experienced this. What I'm told is that your heart is beating really fast, but you're just sitting there. But you really, really just feel your body just full of energy and power. But it's well, that's if you're at rest. And in exertion, you're just you've got like superpowers or something because you got all this oxygen. But if you're resting and you have those oxygen, your heart's just pounding, and you're like, what do I do? I'm just need to sit here and do nothing. So, but oxygen gets toxic after about 1.6 atmospheres. And so what? Why do we care? Well, what do you do if you're scuba diving? So if you increase the pressure up to 4 atmospheres, that means that the partial pressure of oxygen in your lungs is now zero point 0.8 atmospheres. And that's a problem because if you go deeper, you can get oxygen toxicity. And how do you get around this? Well, the people have different tanks. If you go down really, really deep, there is a mixture called heliox. It's a mixture of helium and oxygen at a lower concentration. And that way, it also helps to prevent the bends because the helium does not dissolve in the blood like nitrogen does, but it also prevents death from the toxicity of oxygen. So let's see if you can figure this out. Air is 78% nitrogen. What is the partial pressure of nitrogen at 1 atmosphere? This is supposed to be a softball one. It's A, like that. Okay, so that's it for we got a next section. So see you next time.